So this is the class on chapters 15.1 and 15.2 of Gilbert Strang. So today we're going to cover double integrals. Just an introduction. Alright, so this class is going to be an introduction to double integrals, corresponding to chapters 15.1 and 15.2 of Stewart's calculus. From single variable calculus, you are undoubtedly familiar with integration as a Riemann sum. Right? So the basic idea is this: you have a graph. Sorry for that. Have a graph y equals fx, and let's say you want to find the area beneath the graph from x equals a to x equals b. So you want to find the area of this shaded region. Well, the way to do this is to subdivide, not subdivide, divide this area. Divide the interval AB into a large number of subintervals, and then take. Okay, so let's do the first step, right? So you have AB. So if I divide AB into n subintervals, then the width of each subinterval, let's call that width delta x, is of course b minus a over n, right? And then you take from each subinterval a representative point. Right? So for example, xi star is the representative point from the ith subinterval, right? So you take a point from each subinterval. So you see you have n representative points. We have n representative points. Now this xi star, this could be any point. This is any point in the subinterval. It could be the midpoint of the subinterval. That's entirely up to you. So after you've done that, you evaluate the sum n f of xi star, right, times delta xi, where xi is xi minus xi star is in this interval between xi minus 1 and xi. Now here you let a equal x0 and v equal xn. Okay, so what does this sum give you? This sum gives you a good approximation for the area of the area under the curve, right? F of xi star delta xi, where a is the area under the curve, y equals fx from x equals a to x equals b. So a is basically an approximation for the area. Now, you also know from single variable calculus. Okay, so first of all, why is this an area? Why is this an area? Okay, should be delta x, not delta xi, because the intervals are all the same, right? Okay, so why is this? Why does this give you an area? Let's look at the curve again. With the x, of course, with the axes. Sorry for the crooked line. So this is x equals a, x naught equals a, and x equals b. So let's take the ith subinterval, right? So this is xi, and let this be xi. Let's say this is xi minus 1, and this is your xi, and your xi star is somewhere here. Xi star is somewhere here. Right. So delta x equals xi minus 1. Now, and this height, right? So f of xi star is actually equal to the height of this shape, right? I mean, this is a trapezium. This looks like a trapezium. We will approximate it to be a rectangle, right? Because this delta x is small. Right, so if delta x is small, then this shape here, the shaded region, may be taken to be a rectangle of height f of xi star and width delta x. Then the area may be approximately taken. area is approximately equal to f of xi star delta x. Now you add all of these f of xi star delta x's, and you get this summation, right? So you add all the terms of this form, and you get this summation, this formula for the area, and this is known as a Riemann sum, right? This is what is known as a Riemann sum. Okay, so intuition tells you that the smaller the interval width, subinterval width, the better the approximation for the area. Right, that's what intuition tells you. So the way you make the interval width smaller is by is by increasing n. So we want to increase n, the number of subintervals. Right, so if I do that, if I increase n, if I increase the number of subintervals, then delta x, which is given by b minus a by n, this becomes small. This will make delta x small, right? Increasing the number of subintervals is going to make delta x small. Now, if that is the case, then a good area, so, as n goes to infinity, the Riemann sum approaches the area, the actual area, the exact area. So we say that the area is equals not approximates I is equals so first thing you do is you let n go to infinity, the limit as n goes to infinity, I goes from 1 to n f of xi star delta xi. Right, so this is the basic idea. This is the basic idea of integration. So this is actually equal to again, by definition, a to b f of x dx. Right, so this is the definite integral from a to b. Definite integral of f of x from a to b. And remember, a is equal to x naught and b is equal to xn. Alright, so now I mean of course I'm sure you've come across problems where you have to do Riemann sums to approximate integrals. So now what we're going to do is going to look at Riemann sums of double. We're going to find a way to define double integrals, right? Double integrals, right? So you have, so in this course, right? So instead of curves, you have met with surfaces, right? Surfaces of the form z equals fxy, right? Things that look like something that looks like, so this is x, this is y, this is z, x, y, surfaces that look like this, right? Z equals f of x, y, right? Now, I could very well ask you the following question. What is the volume under the surface z equals fxy with the okay, what is the volume under the surface z equals fxy with the following limits on x and y? Following limits on x and y. For example, x goes from x naught to xn, and y goes from y naught to yn. How do we solve this problem? Let's not call it ym, let's call it ym, right? How are we going to solve this problem? So this defines a region defines a rectangular region on the xy plane, right? So let's look at this region. So let's look at the xy plane now. Okay, so let this be yn. This is your y0. This is your x0. Right, this is your x0. This is ym. And this is xm. Right, so and of course this is the y-axis and this is the x-axis. Okay, so remember volume. What is volume? Volume equals cross section times the height, right? So the cross section, so the shape we're talking about, the shape under the surface. So the shape, we want to estimate the volume, and we want to find the volume of the shape whose cross section is given by whose base is actually given by this shape, right? This is the base of the shape, and the height is z equals f xy. Now, why do we need integration to solve these problems? We need integration to solve these problems because the height is not constant. We need integration because the height is not constant, right? Okay, because otherwise you would have just said volume equals base area times the height, just as you would with a cylinder or with a cube. But since the height is not constant, you do need integration. Now, the idea is the same as it's not the same. I mean, it's similar to this, right? It's similar to Riemann sums in one variable. So here's what you do. First thing you do is you divide. So this is xn. Divide. How do we find the volume? Okay, before that, let me show you the diagram from the book, right? I mean, this is, of course, clearer. The diagram from the book is obviously a lot clearer than any diagram I can draw. Okay, so we want to find the volume, right, underneath this surface, right, and over the following over this domain in R2, right? So this is our domain in R2. They used A, B, C, D. We used x naught, xn, y naught, yn. Right. So they call this region underneath the graph and above, and underneath the surface and above this subdomain of R2. They call this region S. Right. So the idea is to divide. Right. Is to divide. The x interval into, because we're going to divide x into divide x and divide R2. I'm sorry. Let's call this region D. Right. So we want to divide D into small rectangles. And let's say x0 equal, let x0 equal A, xn equal B, y0 equals C. This is my region D, and ym equals D. Right. So D can be written as xy. X is in this interval, AB, and y is in this interval, CD. Right, so now what I want to do is I want to divide D into small sub-rectangles. Right, so D is a big rectangle, so I want to divide D into smaller sub-rectangles. So how many so if I divide AB into n subintervals and CD into m subintervals, if I do this, then I must have mn rectangles. Right, so this AB is divided into n subintervals, and CD is of course divided into m subintervals, right? So let's draw the rectangles. Sorry about that. Dot. Okay, and then you have the divisions on X. These divisions are supposed to be equal with. This doesn't turn out to be a straight line. Okay, so these things should be straight lines. Sorry. Right. So we have mn rectangles. In this region, we have mn rectangles right. So now AB has been divided into n subintervals. So what does that tell me? This tells me that the width of each subinterval, delta x, width D, width of each subinterval, right? That AB is divided into equals B minus A over N, and similarly delta Y equals D minus C over N. Delta Y is the width each subinterval that C comma T is divided into equals D minus C over M. Now notice that the area of each of these subrectangles, right? The area of each of these subrectangles is delta x times delta y. Area of the subrectangle each is delta x times delta y. Now we're going to use that. We're going to use that fact to find the volume underneath the surface S. Right. So let's do a Riemann sum. Right. So this region here, right? This can be each of these rectangles, right, can be each of these rectangles can be identified. These rectangles, they form a grid, right? These subrectangles they form a grid. Subrectangles form a grid, right? And each subrectangle can be identified by two numbers. Each subrectangle can be identified by two numbers. For example, this subrectangle, this is the 1 1 subrectangle. Why is this the 1 1 subrectangle? Because this is the first x interval and the first y interval, right? This one, for example, this is the 2 2 subrectangle. Right? Because this is the second. This is the second x interval and the second y interval. Let's now what we need to do is we need to choose a representative point. Choose a representative point from each subrectangle. So notice something here, right? That we can choose xi star, yj star is as a representative point from the ij sub rectangle. However, I can be anywhere between 1 and n, because x of course is between x is between x0, x1, x2, x all the way to xn, and y and of course j can be anywhere between 1 and m, right? So now, and of course Rij is the ij at subrectangle. Now let's take the ij at subrectangle, right? So let's call, I don't know, let's call this guy. Let's call this guy the ij at subrectangle. Ij subrectangle. Okay, so this is the rectangle which contains. This is the rectangle which contains Rij is defined as the rectangle which has, actually it's not defined as this, it is the rectangle which has xi star and yj star as its representative point. Now notice that when we're doing Riemann sums in single variable calculus, we had representative points of only one variable. Now we have representative points with two variables, xi star, yj star. Now what is the area? What is the now the question is what is the volume under the shape okay, let's not call it the shape, let's call it the surface z equals fxy bounded below by the rectangle Rij, meaning by Rij of course I mean x has to be between xi minus 1 and xi, and y has to be between yj minus 1 and yj, right? This is how Rij is defined, right? Bounded by this rectangle, right? And bounded below by the xy plane, right? So again, volume is what? Volume is equals cross, okay, it's base area times height, right? Times height, right? Now if Rij is small, and by height we mean z value. Now if Rij is small, we can take this height to be constant over Rij. I mean, we can take this z value to be constant over Rij. Now, if that is the case, then we take the height to be equal to the representative point, right? So the height equals z equals f of xi star yj star, right? That's your height. So the volume above that rectangle Rij should be equal to f of xi star, f of xi star, comma yj star times the base area delta x delta y. So this is the volume above Rij. Now the total volume above D, the total volume above D is then total volume above the domain D. I mean, by total volume above D, I mean the total volume bounded below by D, bounded by D, and of course below by the xy plane. This is approximately equal to, I mean, all of these, sum of all of these volumes, right? So that is approximately equal to I going from 1 to so I goes from 1 to n, and j goes from 1 to m, right? Xi star yj star delta x times delta y. Now, what happens if we increase the number of intervals, right? As the number of intervals increases, as m and n increase, right? So as m and n, the number of intervals, right? The number of subintervals increases. We have the approximation gets better and better, right? So so then the exact volume this is equal to the limit as n goes to infinity and m goes to infinity, I goes from 1 to n, j goes from 1 to m, f of xi star yj star times delta x delta y. This is the volume that we get, right? Now this is defined as the by definition this is equal to the double integral f of x y dx dy by definition, right? This is by definition equal to this. Now what does this mean? This means that you do this integration first, right? This bit first. You do the integration in brackets first. Integration in brackets first by holding y constant. Right? You hold y constant and you do the integration in brackets first. This is just like, in partial derivatives where you hold y constant when you're doing the derivative with respect to x, right? So you do the integration in brackets first, and then after you do this integration, right, you'll get a function. The thing that you'll get, ab f of xy dx will give you a function of y only, right? Let's call it g of y, right? Some function gy. Then what you do, you integrate g of y dy, right? And then you get your answer. So this is actually equal to g of y dy. Let's look at a few examples, and okay, so let's say this is an example of a Riemann sum, right? So estimate the volume of the solid that lies above the square R, so above this square. So this is my domain. This is my domain D, right? Below the elliptic paraboloid, z equals 16 minus x squared minus 2y squared. So f of xy is this. Divide R into 4 equal squares and choose the sample point to be the upper right corner in each square, Rij. So if I divide this domain into 4 equal squares and I choose the sample point as the upper right corner, then my sample points are 1 1, 1 2, 2 2, and 2 1. Okay, great. So we want to approximate the volume, right? I want by finding the volume of boxes, right? Basically, that's what we're doing. We're finding the volume of boxes with constant height. So the Riemann sum is, of course, is then I equals 1 to 2, j is equal to 1 to 2, f of xi star. You could use xi, you could use xi star. That's up to you. Yj star delta x delta y. So delta x delta y is the area of a rectangle of these sub squares or sub rectangles. So we call it delta a, right? So you write out the double summations: f11 delta a plus f12 delta a plus f21 delta a plus f22 delta a. So f11 is of course equal to 13, f12 is 10, is 7. You just plug this in. F12 is 7. F21 is 10, and F22 is 4. And delta is, of course, 1 times 1, which is 1. So you get 34. So the approximate volume, if you use 4 subintervals, is 34. And notice what happens is if you use more and more boxes, right? So for example, if you use 16 subintervals, right? For if you use m equals n, m equals 4, n equals 4, then the volume is 41.5. If you use m equals, so this is what the volume looks like, right? If you use m equals 4, n equals 4. If you use m equals 8, n equals 8, this is what the volume looks like. This is approximately equal to 44.875. If you use m equals n equals 16, then you get 46.46875. So get better and better. Get better and better estimates of the volume under the curve, under the surface. I'm sorry. So let's see how we can approximate. Let's see how we can approximate this integral, right? 1 minus x square dA, right? So of course, so this is actually equal to so this is actually equal to the dA, since x goes from -1 to 1 and y goes from -2 to 2, so we may write this integral as -2 to 2 square root of 1 minus x square d, sorry, this is -1 to 1, right? This is dx dy. Now this integral is not, I mean, we can compute this integral, but it's not always the easiest integral to compute. So here's what we can do. Square root of 1 minus x square is greater than 0, right? Notice that this surface, right, over this domain, this function, f of xy equals the square root of 1 minus x square. Over this domain, meaning x goes from -1 to 1 and y goes from -2 to 2, is actually this half cylinder, right? It's the part of the cylinder that lies above the xy plane, right? It's the part of the cylinder that lies above the xy plane. So z equals the square root of 1 minus x square. Is basically a half cylinder. Is a part of the cylinder that lies above the xy plane, whose axis is the y-axis. Right, the axis of the cylinder is the y-axis. So we could easily find this integral by finding the volume of the cylinder, half the volume of the cylinder. Right. So y goes from -2 to 2. So the radius of the cylinder is 1. The height of the cylinder is radius of cylinder equal to 1, and the height equals 2 minus 2, which is 4. So the volume is half pi r square h, which is twice y. So this is actually equal to twice y. So this is one way of doing it. I'll tell you what. Let's try to evaluate. Actually, how much do we have left here? Right. So we will be looking at Fubini's theorem, and that should be the end of that. Right. So we'll look at Fubini's theorem after this, and okay. So let's try. Let's see if we get the same answer. Let's see if you get twice pi. If if we evaluate with our standard methods, right? So we have negative 2 to 2, negative 1 to positive 1, square root of 1 minus x square dx dy, right? So what is this equal to? Negative 1 to 1 minus x square dx, right? So how do we evaluate this? So you let x equal sine theta, right? And so of course this becomes negative pi over 2, right? To pi over 2. So this is 1 minus sine square theta, cosine square theta. So take the square root, you get cosine theta, and dx equals cosine theta d theta, right? So see, we have to evaluate minus 5 2 cosine square theta d theta. This is the same as 2 times 5 2 square theta d theta. It's because this is an even function. Now cosine theta is an even function, so cosine square theta is an even function, right? So so remember, cosine 2 theta equals 2 cosine square theta minus 1 square theta minus 1. So this can actually be written as 2 pi over 2 1 plus cosine 2 theta divided by 2 d theta, and this is of course equal to so you have these cancel out, so theta plus half sine 2 theta, go from 5 over 2 0, right? And of course you get 5 over 2, right? So you have 5 over 2, so this gives you 5 over 2, so this should then be equal to minus 2 to 2 5 over 2, right, dy. But this is actually with this is a constant, right? So I could take this 5 over 2 out, times 4 equals twice phi, and you get the same answer, right? This is what we were expecting. It's exactly what we were expecting. So this is an example of how you can evaluate these integrals. I want you to look through example 4, right? Look at example 4. Now, this is an extremely important theorem in integral calculus. This tells you that basically, it's called Fubini's theorem. It tells you that it doesn't really matter in what order you evaluate it. I mean, if a function satisfies certain properties, it doesn't really matter in what order you evaluate those integrals, right? So if f is a certain property, meaning if f is continuous on this rectangle, r equals this rectangle, right, then this integral fxy dy dx is the same as this integral fxy dx dy. Notice that we flip the integral. So meaning Fubini's theorem basically tells you Fubini's theorem, if f is continuous on, if f is continuous on this interval CD, then we have dy dx equals CD, then this is true. F of x y dx dy. Now, what does this tell you? This tells you basically that it doesn't really matter if you do the x integral first or the y integral first. It does not really matter. Whether you do the x integral first or the y integral, right? It doesn't really matter if you do the x integral first or the y integral. The result is the same. Now, we're not going to go into proof of Fubini's theorem, but we're going to look at a justification. Why do we think that Fubini's theorem is justified? So let's look at the truth of Fubini's theorem in the case where f of xy is greater than or equal to 0. Now, the integral, this integral, right? What does this give you? This gives you the volume of a solid, right, that lies above R, above the rectangle R, under the surface that equals fxy. Okay, so let's look at another way we can interpret that volume. So volume is actually the area, this cross-sectional area, the integration of this cross-sectional area from x equals a to x equals v. It's basically this cross-section, right? Integrated from x equals a to x equals v. And the curve C, whose equation is z equals fxy, where x is held constant, and C and y is between C and D. But this area, this thing, this can be this is actually equal to the area underneath the curve, right? So the area underneath the curve. So for this curve, x is held constant, y goes from C to D. So the green area can be written as this integral, because x is constant now, right? So you have this volume equals v, which is equal to avx dx, which is equal to this. Now similarly, if I use a perpendicular cross section, right, I can approximate ay. I can write that volume is equal to a to c to d ay dy, and I could write ay equals some ay equals a to v f of xy dy, right? So then the volume would be equal to c to d a to v f of xy dy as I'm sorry, a to v f of x by dx, sorry, right, because y is held constant, right? So dy, ay dx. So this is dx. This should be dx times dy, and that is the same as this guy. These two expressions represent the same volume, right? So this is intuitive justification. This is not a full proof, right? This is intuitive justification. Okay, so now let's look at a few examples of Fubini's theorem, and we'll look at iterated integrals. Okay, so let's see where in some cases, of course, Fubini's theorem makes evaluating integrals a whole lot easier. So let's see where that is the case. So we have this double integral, right? And of course dA, remember dA is dx times dy. Okay, so x minus 3y squared dA. Okay, so and x goes between 0 and 2, and y goes between y is between 1 and 2. Alright, so so x goes between 0 and 2, y is between 1 and 2, x minus 3y squared. So let's try to verify Fubini's theorem for this example. X minus 3y squared, x goes between 0 and 2, y goes between 1 and 2. dx dy. Okay, let's evaluate this. Right. So first thing we do is we'll evaluate the inner integral first. So this guy gets integrated first. So this gives you half x squared minus 3y squared x, and remember x is between 0 and 2 dy. 1, 2. So this is 4 by 2, which is 2. Okay, so 4 by 2, which is 2, minus 6y squared dy. This gives me 2y minus 2y cubed, and y of course goes between 1 and 2. 4 minus 8 minus 2 minus 2, which should give you negative 4. I think I'm making a mistake somewhere here. The answer should be minus 12. 1 to 2 dy, right? dy is between 1 and 2. Wait, just give me a moment. Half x squared minus 3y squared x. 4 by 2 is 2 minus 6y squared. Okay, so you have 2y minus 2y cubed. 4 minus 8 minus 2 minus 2. How do you get minus 12? X 3y square. Okay, 2 minus 6y square. I think I made a mistake in the last step. 4. Sorry, x equals 1, right? So 2y minus 2y cubed. Oh, sorry, this should be 16. This should be 8. This should be 16. Minus 16. Alright, sorry about that. So this should be minus 12. Right, now let's see if let's see what happens when I reverse the order of the integrals. Right, meaning if I do dy dx, what do I get? So if I have 1 to 2, 0 to 2, x minus 3y squared dy dx. Let's see what happens here. So you do the so you do the y integral first, right? You do the y integral first, 0 to 2, so you have xy minus 3y cubed by 3, so this is y cubed. And of course you do the integration from 1 to 2. I'm sorry, this is x equals 2. So this is y equals 2 y is equal to 1, right? Okay, so 0 to 2, and this is going to give you a function of x, alright? So this is going to be twice x minus 8 minus x plus 1 dx, and this is equal to 0 to 2 x minus 7 dx. This is equal to half x square minus 7x, x equals 2, x equals 0, and this is equal to 4 by 2, which is 2, minus 14 minus 0 minus 0, which is exactly equal to minus 12. So it didn't really matter which order we did the integrals in. Alright, we still got the same answer. Notice how Fubini's theorem is similar to Clairaut's theorem, right? Fubini's theorem. What is Fubini's theorem? It's basically C to D f of xy dy dx equals f of xy dx dy. And what is Clairaut's theorem? xy so Clairaut's theorem tells you that it doesn't really matter in what order you do the partial derivatives, and Fubini's theorem tells you that it doesn't really matter what order you do the integration. It's all the same. Right, so so you could look at a few further examples. Example 6, look through it yourself. Example 7 is a volume problem. Alright, so if you you are given the you're given the rectangle, you're given the domain over which to find the volume, and you're given the function. Now what you have to do here is you have to take z to be a function of x and y. So z equals 16 minus x square minus 2y square. So you do the double integral. The volume equals, of course, so the volume equals f of xy dA. Of course, dA is dx dy over the region, which is okay. So bounded by the elliptic paraboloid, the planes x equals 2 and y equals 2, and the 3 coordinate planes. So you have to figure this out, that we're talking about the square 0 2 cross 0 2, right? So this square, you have to figure this bit out yourself, right? So now you do the integration and you get the volume. Okay, and then and this one last thing. Fubini's theorem. This one application of Fubini's theorem, right? So consider a case where f of xy can be factored into two functions, right? One of x and a function of x and a function of y, right? So what happens then? A function of x and a function of y. So let's say if you can write f of xy equal to some g of x times h of y. If you can do that, then AV CD, right? F of xy dy dx equals AV CD g of x h of y dy dx. Now gx is a constant when it comes to gx is a constant when it comes to integration with respect to y. Now since that is the case, we can write this as this integral, we can write this as AV gx CD hy dy dx. Right? So now hy d this guy, right? CD hy dy is just a number, right? It's just a constant, right? So this can therefore be written as CD hy dy times AV gx dx. You can write this as a product of two. If you can factor a function of x and y into functions of x and functions of y, you can write the double integral as a product of two integrals. Right? So take this. This is the x dy. Okay, right. So an integral y is a constant, so you could take this hy out. Yeah. So this is what you get when you can factor fxy into gx hy. This is what you should get. Now let's look at this example, example 8. So rxy equals sine x cosine y dA, and the integration range is 0 to 5 by 2 for x. This is the x range, 0 to 5 by 2 the y range, right? So this is equal to sine x, so this is your gx and this is your hy, and you evaluate the product of these two integrals, and that's how you integrate. Okay, we'll look at one application of double integrals, which is average value. So in single variable calculus, you are used to finding the average value over a range of values of x. Range of values of x, right? So average equals 1 over v minus a dx, right? So when you talk about functions of two variables, the domain is of course an area, right? So domain is the domain is an area, right? So the average value of a function of two variables over domain R is average, and domain R is this domain AV cross CD equals 1 over the instead of the length, what you get is 1 over the area of R, right? Area of R times the integration. I should write this more clearly. 1 over the area of R times the integration fxy, so AV, this is dx dy. So this is the average value of a function of two variables over a domain R. Right, so you could you could use the average value, of course, to find the area if the average is if f is greater than 0, and yeah, just plug it in, plug in the value, plug in the function and the area, and you can get the average value. So that's it for section 15.1, right? So that took quite a while, but hopefully section 15.2, which is double integrals over general regions, basically this chapter is calculating integrals, double integrals, triple integrals. So please don't be too concerned about the length of this chapter. It's everything here is obviously related to one thing is related to the other, but this chapter is mostly calculations, right? So just you know how to calculate areas and volumes and things like that. So it should not trouble you that much. So So we'll discuss this in. Hopefully we'll discuss this. What we've done here on Wednesday, inshallah. Okay. Thank you very much.